Travelling faster than light and travelling backwards in time are the same thing. Today I'm going to prove that to you. Faster than light travel is, understandably, a staple of science fiction. The reality of the vast scale of our universe, even of our galaxy, is inconvenient for tales of star-hopping adventure or warring galactic empires. Enter the warp drive, and hyperspace, and stargates, and the infinite improbability drive. Plenty of ways to make travelling across impossible distances as challenging as a weekend road trip. And sci-fi makes instantaneous communication a breeze, with Ansibles, Sophons, subspace relays, and tachyonic anti-telephones. Actually, that last one is a thought experiment that demonstrates that if you communicate using tachyons, hypothetical faster than light or superluminal particles, it's possible to receive a reply to your message before the message is sent. By choosing the right path and the right reference frame, any superluminal motion can lead to information or objects returning to their origin before they depart. Today, I want to show you how to navigate such a path. To do that, we're going to need a map. We'll do this in flat space, so we need a flat or Minkowski space-time diagram. We're going to add space-time interval contours. We've spent some time talking about how these contours define the flow of causality. If you aren't familiar, you should probably watch that episode first. In addition, today's episode is going to answer the recent Time Warp Challenge question, so spoiler alert. In the olden days, before Albert showed us the way, time was thought of as universal. It was assumed that the entire universe exists simultaneously in a state of now, and that all points move forward in time at a constant rate for all observers, governed by one global clock. In the olden days, the same time axis of a space-time diagram would apply to everyone, but no longer. Einstein showed us that there is no universal clock. Instead, every space-time traveller carries their own clock. The tick rate of your clock and your perception of simultaneity depends on your velocity. There's no absolute notion of velocity, so everyone can be considered motionless from their perspective. Everyone draws their space-time diagram time axis parallel to their direction of motion because that's their experience of stillness. The tick marks on that time axis also depend on velocity and represent the speed of everyone's personal clock, their proper time. And everyone also has a different space axis, representing chains of simultaneous events according to their perspective. Those axes reflect symmetrically around this 45-degree path, representing the unvarying speed of light. Connect the ticks of all possible time axes and you get these nested hyperbolae. These are contours of constant space-time interval. A straight line journey to any location on one of these contours seems to take the same amount of proper time for every traveller. The space-time interval is special because every traveller will agree on which contours a set of different events lie, even if they don't agree on the temporal ordering of those events. If we write the space-time interval for flat space with a negative sign in front of the time part, then changes in your space-time interval have to be negative, as long as you travel at less than the speed of light, so greater than 45 degrees on the diagram. Each contour is smaller than the one before, and so forward temporal evolution means rolling down the causality hill. On the other hand, superluminal paths at less than 45 degrees, mean revisiting previous contours, travelling uphill. That uphill journey is equivalent to time travel. To prove it, let's think about the scenario that I proposed in the recent challenge question. It went something like this. You're in a race to claim a newly discovered exoplanet 100 light years away. Your competitor immediately launches a 50% light speed ship, the antimatter-powered Annihilator. You decide to wait, taking a century developing an Alcubierre warp drive. Your ship, the Paradox, can travel at twice the speed of light. Let's see what that looks like on the space-time diagram. We'll plot the world lines of these ships as recorded by someone waiting back on Earth. Earth doesn't move from its own perspective, it just hangs out at x equals 0 and rolls upward in time. The Annihilator races off towards the exoplanet, 100 light years this way. At 50% light speed, the Annihilator would take 200 years to reach its destination, from Earth's perspective. Meanwhile, your own world line remains on Earth as you build the Paradox. However, when you launch, you travel at twice the speed of light, and so you reach the exoplanet in 50 years from launch date, also from Earth's perspective. You overtake the Annihilator at around the 67 light-year mark and finish the race 150 years after the race began. Congrats, you win. I just hope your rejuvenation tank is still working. But winning was never the question. I'm really curious about what the crew of the Annihilator sees at that moment you pass them. Do they perceive you as traveling in time? And now that you've mastered faster than light travel, can you pilot the Paradox back to a point before the race even started? To see what the Annihilator sees, let's transform the space-time diagram to their perspective. In fact, we need to do a Lorentz transformation. Their time axis is their own world line, and their space axis is symmetrically reflected around the path of light. Now, add hyperbolic space-time interval contours. These are the space-time intervals as calculated from the 0 point in space and time, the beginning of the race. Because the space-time interval is invariant to Lorentz transformations, when we shift to the velocity frame of the Annihilator, we just make sure events stay on the contours that they started on. The Annihilator perceives itself as stationary and sees Earth racing away in the opposite direction at half light speed, while its destination races towards it at the same speed. We can figure out the Paradox world line because we know which space-time interval contours it's on when it departs from Earth and arrives at its destination. The Paradox still appears to be travelling forward in time with respect to the Annihilator, even though it's travelling faster than light. But what does this look like to the captain of the Annihilator? Well, you just trace the photon paths, assuming for a moment that an FTL ship doesn't produce infinitely red or blue shifted photons. The Paradox outraces its own photons as it catches up to the Annihilator, and then it continues to emit light backwards behind it after it passes. So the Annihilator sees a series of photons coming from both directions that arrive simultaneously. The Paradox appears to materialize out of nowhere and then proceeds to split in two. One Paradox seems to race onwards towards its destination, while the other travels in reverse back towards Earth. Now that looks a bit like time travel, but a physicist on the Annihilator would still infer that the Paradox is moving forward in time, upwards according to the Annihilator's own time axis. However, there are perspectives where time travel seems real. Let's look at the perspective of a different space-time traveller, one travelling at very near the speed of light. When we transform the diagram to their perspective, we see that the Paradox really does appear to travel backwards in time according to this new time axis. But this is just perspective, right? Well, no. Not if we can find a way to bring the Paradox back to a point in space before it was built. To do that, we first need to outrace photons that were emitted at the space-time point that we want to proceed. In this case, it's the start of the race. Let's return to the reference frame of the Earth to do this. We can keep flying the Paradox until we cross this ominous 45-degree boundary. Let's fill in the space-time diagram with all four quadrants. These ones represent the regions inaccessible for sub-light speed travellers starting at the origin. Now we transform back to the near light speed reference frame. In that frame, the Paradox has moved into a region that appears to be prior to the start of the race. If we assume that this trajectory is valid, then there's no limit how far into the past we can travel. If we travel far enough, then when we finally turn the Paradox around, its twice light speed movement will take us back to the beginning of the race, long before the Paradox was ever built. This seems like a trick, and it sort of is. We constructed this time-traveling path using two different reference frames. In this case, Earth's, and then a near light speed frame. Normally, that would be fine because space-time events marking the different stages of a sub-light speed journey transform consistently between these frames. However, when we introduce faster than light travel, things get messed up. Superluminal paths aren't real world lines. Real world lines don't point backwards in time under Lorentz transformations. While we can define a chain of events that looks like an FTL journey, these aren't paths that real objects can take. And that includes us. Remember, we are temporal creatures. Our experience of the universe is a thing that emerges from the forward causal evolution of the matter that we're composed of. Reverse the flow of time, and you reverse the flow of you. Even our fantasies of time travel are just another pattern emerging from our one-way trajectory through the temporal part of space-time. Thanks to everyone who submitted answers to the Time Warp Challenge. If you see your name below, we randomly selected your correct answer to win a Spacetime t-shirt. Shoot us an email at pbsspacetime@gmail.com with your mailing address, US t-shirt size, small, medium, large, etc., and let us know which of these tees you'd like. Also, it's that time of year again. Time for the annual PBS Digital Studios survey. This is not a graded quiz, nor will it tell you which Disney princess you are, but it will really help both Spacetime and PBS figure out what you guys are into and what you want for the future. Click on the link in the description to fill out the survey. It should only take about 10 minutes, and we'll be giving away PBS shirts to 25 randomly selected participants.